In episode 20, titled Dynamic Routing Overview, What Changes When Routes Must Adapt, we frame dynamic routing as automated learning with a real control plane cost, because you gain adaptability by adding a conversation between routers that must be designed and governed. The exam often presents dynamic routing as the natural next step after static routing, but the more important lesson is what changes operationally when devices start learning routes automatically. With static routes, intent is written down explicitly and changes require humans, while with dynamic routing, intent is expressed through rules and policy, and devices update reachability on their own. That shift can be a major advantage when networks grow and change, but it also introduces new failure modes, new security considerations, and new troubleshooting patterns. If you understand the core behaviors, you can read scenario cues and decide whether dynamic routing is the best answer or an unnecessary complexity. The goal here is not to memorize protocol details, but to understand the architectural implications of letting the network adapt. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. At the heart of dynamic routing is the concept of neighbors exchanging routes based on rules and metrics, which means routers form relationships and share information about what networks they can reach. Neighbor relationships are how routers decide who they trust to send routing updates, and they usually depend on adjacency on a link or on a configured session over a path. Routes are exchanged as information, not as physical paths, and each router uses protocol rules to decide which routes to accept and how to compare competing options. Metrics are the scoring system that helps routers choose the preferred path when more than one route to the same destination exists. The precise metric definitions vary by protocol, but the architectural point is that route choice becomes a function of policy and measured cost rather than of fixed human entries. In scenario terms, when the prompt mentions multiple links, alternative paths, or automatic failover, neighbor route exchange is the mechanism that makes that behavior possible. Understanding this neighbor and metric model helps you interpret answers that talk about automatic route learning and path selection. Convergence is the concept that describes how long it takes the routing system to recover after failures or changes, and it is one of the most exam-relevant characteristics of dynamic routing. When a link fails or a route becomes invalid, routers must detect the change, communicate it to neighbors, and compute new preferred paths, and until that process settles, traffic can be disrupted. Fast convergence is valuable for availability because it reduces outage time, but it can also increase control plane chatter and sensitivity if not tuned carefully. Slow convergence reduces control plane activity, but can leave the network in a degraded state longer, which is unacceptable in environments with tight recovery expectations. The exam often hints at convergence needs by describing how quickly the network must recover from failures, whether downtime is tolerated, and whether users experience intermittent black holes during changes. Convergence also explains why a network can appear unstable during transitions, because partial knowledge can exist temporarily while updates propagate. When you keep convergence in mind, you can choose solutions that match recovery expectations rather than solutions that only look good when everything is healthy. Scalability is where dynamic routing often earns its place, because when many networks must stay consistent, manual static updates become error-prone and slow. As organizations add sites, add segments, or integrate cloud networks, the number of routes that must be coordinated grows, and static routing starts to behave like a fragile spreadsheet that needs constant updating. Dynamic routing allows a new subnet or a new site to be learned automatically, reducing human coordination and reducing the risk of missing return routes that create one-way failures. It also supports more complex topologies, such as partial mesh or multiple redundant links, where manual route management quickly becomes unmanageable. In exam scenarios, when you see multi-site growth, frequent additions, or a need for consistent reachability across many segments, dynamic routing is often favored because it aligns with scale and change. The core idea is that dynamic routing shifts work from humans to the control plane, which can improve consistency when done well. It is not that static routing is wrong. It is that static routing does not scale safely when change frequency rises. Route loops are one of the classic risks because if routers have inconsistent information, traffic can circulate without reaching its destination, and dynamic routing protocols include mechanisms to prevent this. A loop is often created when routers believe a path exists through each other, but the path is actually broken, causing packets to bounce back and forth. Loop prevention mechanisms vary by protocol family, but the architectural concept is that protocols include rules that detect and avoid routing information that could create circular dependencies. These mechanisms often involve tracking where a route came from, limiting how long incorrect information can persist, and ensuring that routers do not prefer paths that are logically impossible. The exam does not always ask you to name specific mechanisms, but it expects you to understand that loops are a control plane failure mode and that protocols have protections that influence convergence and stability. When a scenario describes traffic disappearing or networks becoming unstable after a change, loop-related behavior is one possible explanation. Recognizing loop risk helps you appreciate why dynamic routing adds both power and complexity. Policy control is where dynamic routing becomes architecture rather than automation because policy shapes which routes get advertised and which routes get preferred. Advertising control determines what reachability information a router shares with neighbors, which matters for security, segmentation, and reducing unnecessary route spread. Preference control determines which path is selected when multiple routes exist, which can be used to steer traffic, balance load, or enforce that certain links are used only as backups. Policy also helps prevent accidental exposure, such as advertising internal management networks into places where they should not be reachable. In hybrid environments, policy is essential because different segments may have different trust levels and different ownership, and uncontrolled advertisement can violate those boundaries. The exam often hints at policy needs with phrases like, "Only certain networks should be reachable," or "Prefer this path unless it fails," and dynamic routing answers that include policy awareness tend to be stronger. The main point is that dynamic routing is not just letting routers talk, it is controlling what they say and how they decide. Redistribution is a place where many real networks get into trouble, and the exam sometimes tests redistribution pitfalls when mixing protocols across environments. Redistribution means taking routes learned in one routing protocol and injecting them into another, which is common when integrating different domains or when bridging on-premises and cloud networking models. The risk is that you can create unintended reachability, route feedback loops, or conflicting metrics that cause unpredictable path selection. You can also accidentally import too many routes, bloating tables, and increasing convergence time, which affects stability. Another pitfall is losing policy context, because a route redistributed from one domain might not carry the same trust assumptions or filtering expectations into the next domain. In scenario questions, If the prompt mentions mixing routing protocols or connecting environments with different routing models, redistribution risk should be part of your evaluation. The best answer often emphasizes careful control, filtering, and clear boundaries when redistribution is unavoidable, rather than treating it as a simple toggle. A scenario that favors dynamic routing is multi-site growth, where new networks are added regularly and where redundant links exist for resilience, because automatic learning reduces operational friction and improves recovery behavior. In this scenario, each new site adds subnets that must be reachable from other sites, and static route updates across many routers become a frequent source of mistakes and delayed deployments. Dynamic routing allows new site prefixes to be advertised and learned according to policy, and it allows failover to alternate links when the primary path fails, supporting availability goals. Convergence becomes the critical metric here, because the business expects connectivity to recover quickly when a link drops. Policy control also matters because not every site should necessarily reach every network, and dynamic routing allows selective advertisement rather than an all-or-nothing approach. In exam reasoning, the best answer in such a scenario often aligns with dynamic routing because the environment's change rate and redundancy needs make manual routing unsafe and slow. The key is that dynamic routing matches growth and resilience demands when properly governed. A scenario that avoids dynamic routing is one where operations need maximum simplicity, the topology is stable, and the number of routes is small enough that manual control remains safe and well documented. Some environments prioritize predictability above all, especially when staffing is limited, when audit requirements demand strict change control, or when the network rarely changes. In such a case, adding a dynamic routing control plane might introduce more risk than benefit, because misconfigurations, unexpected advertisements, or misunderstood defaults can cause broad reachability changes quickly. Static routing can be easier to reason about and easier to lock down when paths are straightforward and unlikely to change. The exam often includes these cues by emphasizing limited staff expertise, strict governance, or a single-path topology where dynamic adaptation is not needed. Avoiding dynamic routing here is not a rejection of automation. It is recognition that automation has a cost that must be justified. The best answer matches the routing approach to operational reality and change frequency, not to theoretical elegance. One pitfall is default settings causing unexpected reachability changes, because dynamic routing protocols can advertise more than you intend or prefer paths you did not anticipate if you do not apply policy explicitly. A router might begin advertising connected networks automatically, or it might learn a route and prefer it based on metrics that do not match their business intent. This can lead to sudden reachability between segments that were previously isolated, or it can shift traffic onto links that are not sized for the load. The danger is that the change is correct according to protocol rules, which makes it feel mysterious when you expected a different outcome. This is why policy control is not optional in most environments, and why documentation and review are essential when dynamic routing is introduced. In exam scenarios, if the prompt describes unexpected access appearing after enabling routing, default advertisement and preference behavior is often part of the story. A strong answer acknowledges the need to control what is advertised and how routes are selected, rather than simply saying, "Enable dynamic routing," and assuming it will behave as desired. Another pitfall is weak authentication, allowing routing misinformation in, because routing protocols are part of the control plane, and control planes are attractive targets. If a malicious or misconfigured device can form neighbor relationships and advertise routes, it can redirect traffic, create black holes, or expose internal networks by altering reachability. This is especially risky in shared environments, in hybrid designs with multiple administrative domains, or in networks where physical access is not tightly controlled. Strong authentication and neighbor control reduce this risk by ensuring that only authorized peers can participate in routing exchanges. Even without naming specific cryptographic methods, the exam expects you to recognize that routing updates should not be accepted blindly. When scenarios mention untrusted segments, partner connectivity, or unexpected routing changes, weak neighbor security should be considered as a plausible cause. The best answer typically includes the idea of securing routing exchanges and limiting neighbors, because the routing system is a critical trust boundary. A memory anchor that keeps the core ideas together is neighbors, metrics, convergence, policy, loop prevention, because these are the features that define how dynamic routing behaves in practice. Neighbors remind you that routers must form relationships and exchange information, and those relationships must be controlled. Metrics remind you that path selection is based on a scoring system that can favor one link over another and that may need tuning to match intent. Convergence reminds you that recovery time after failures matters and that the control plane must settle before traffic is stable again. Policy reminds you that advertisement and preference must be shaped so reachability matches segmentation and business needs. Loop prevention reminds you that protocols include safeguards, but those safeguards influence stability and are part of why dynamic routing is more complex than static entries. When you can recite this anchor, you can quickly evaluate whether a scenario needs dynamic routing and what risks to mention. It also helps you identify which answer choices are missing key considerations, such as proposing dynamic routing without any policy or security control. To end the core with a selection prompt, imagine a set of constraints where the organization expects frequent additions of new subnets, has multiple links between sites for resilience, but also has limited operations staff and strict segmentation requirements. Dynamic routing can satisfy the growth and resilience needs by learning and adapting routes automatically, but it must be paired with clear policy to limit advertisements and to keep segmentation intact. If operations staff is limited, the design should emphasize simplicity within dynamic routing, such as a controlled routing domain and minimal redistribution, rather than a complex mix of protocols. If strict segmentation is required, policy must ensure that only intended prefixes are shared and that management networks remain constrained. In this scenario, a pure static approach risks becoming unmanageable and error-prone as growth continues, while a poorly controlled dynamic approach risks unexpected reachability changes. The best exam answer is usually the one that chooses dynamic routing for scalability and recovery while acknowledging the need for policy, monitoring, and secure neighbor relationships. This is the pattern of reasoning the exam is looking for. Adapt where needed, control where risky. In the conclusion of Episode 20, titled Dynamic Routing Overview, What Changes When Routes Must Adapt, the central behavior change is that routers learn and adjust reachability automatically through neighbor exchanges, which provides scalability and faster recovery, but adds control plane complexity. Neighbors share routes, and metrics influence preferred paths, and convergence describes how quickly the network stabilizes after failures or changes. Dynamic routing scales better than static routing when many networks must stay consistent, but it introduces risks such as loops and unexpected path shifts if policy is not applied carefully. Policy control shapes what is advertised and what is preferred, and redistribution across protocols can create feedback loops and unintended reachability if not tightly managed. You watch for pitfalls like default settings causing surprising connectivity and weak authentication, allowing routing misinformation into the control plane. Assign yourself one convergence concept recall by taking a simple failure, such as a link drop, and narrating what must happen for the network to detect the failure, update neighbors, select new routes, and restore stable traffic. Because that narrative is the practical meaning of convergence the exam expects you to understand. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.